Hello. We'll talk about hash functions now. So a hash function actually consists of two functions, a key generation function gen and an actual hash function h. Then the idea is you generate a key s, then you have this function h of s, and then the security property that we wanted from this is collision resistance. Meaning that if we generated this key s using the key generation algorithm, and then we give that to some adversary, then the probability that A will be able to output x and x prime so that they are not equal, but their hash values are the same. This whole game should be hard for A to win. So A should be able to find two different x's that hash to the same value. So what I want to discuss is this key here, this s here. It's kind of a weird thing. So we've seen one-way functions and pseudorandom generators. And they had no key at all. Then the things that had keys were, for example, encryption schemes and pseudorandom functions. And they had a secret key. You wouldn't be able to give this key to an adversary and still claim security for anything. And we've seen signature schemes that have public keys and secret keys. And we will also later see encryption schemes that have public keys and secret keys. But also there was kind of a secret involved. So now the question is, why is this a thing? So this key S here, it's not secret, so it's not, and there's no secret in this, so it's not one of those, and it does have a key, in contrast to like one-way functions or PRGs. This one actually just only has a public key, which is kind of weird. So why is this? Couldn't we also just like say that we don't have this key generation algorithm and we just, we don't have this S? Okay, let's try it. Let's see what happens. So we change the collision finding game. We don't choose this S anymore, and the S won't be necessary for hashing anymore. So let's say we just have a function h. Like we also had like functions g for PRGs or f for one-way functions. And then we just run A through this game, and if A is able to output a collision for h, then he wins. So I will call this function h collision resistant. If for all adversaries that are probabilistic polynomial time, of course, the probability of winning this hash collision game against the hash function h should be negligible. So what's the problem? Take a second to think about it, if you don't already know. So let's solve it. Essentially, the problem is that I can easily come up with an adversary A that makes this untrue. Well, I can prove this to you. I know that H, which has like an infinite domain and just hashes to values of length n, L of n, I know that collisions exist, right? So there are way too many pre-images for way too few images to fit all of them. So like mathematically, those exist. So I can write that there exists x1, x2. If you know what the pigeonhole principle is, that's it. Okay, so these things exist. So then I can also just construct my adversary A to just output x1, x2. Good. I can obviously write code for A. I mean, I can't personally, but like mathematically, code for A exists that just outputs x1, x2 for this one example collision that exists. And then, well, the chances of A winning this game is just 1. He just wins. So that's clearly not negligible. So why does this S thing solve all of this? It solves it because now you can't do this trick anymore. Now you don't actually know what function you're going to get when you're in the hash collision game. So let's undo this. In this game, so with the key S, yes, it's true. For every HS, this function is not injective. So similarly to here, such collisions exist. However, I don't know which S I'm going to get when I construct my adversary, because the orders construct adversary, run through the collision finding game, and within the collision finding game, I get a random S. So I really don't know for which of these functions to hardcode a solution. So with the key S, there's actually a chance for this for such collision-resistant hash functions to exist. So yeah, as we just talked about, in theory, this key S is like really crucial because no single function is collision-resistant in this sense. I need some sort of unpredictability in the security definition. And if we think about the other things that didn't have a key, like one-way functions and PLGs, those only work because the unpredictability factor in their security games, that's the input to those functions. So the input to one-way functions needs to be random. That's the randomness that's involved there. The input for pseudonym generators is also random. So essentially something needs to be random, otherwise like none of this makes sense. So that's the theoretical realm. If we actually go into practice, then there is no explicit key S. So if you look at SHA-2 and SHA-3, which are kind of the state-of-the-art hash functions that you should use right now, it's not like if I set up my hash-done science scheme with SHA-2 that I will choose like a key for it, but everyone just uses the same function. Okay, if I tell you SHA-2, you already know exactly what function I'm talking about. There's no like S that I need to tell you. And if you want, you can think about it as like having a hard-coded key. So someone designed these hash functions kind of with a key that they chose at design time. And now all of us, we are currently in this huge experiment, this huge security experiment of collision finding for SHA-2 and SHA-3, where someone at some point generated this S, and now it's just valid for the whole world. Of course, that's not necessarily how those keys were designed, so they aren't necessarily chosen randomly. There are some constants in SHA-2 and SHA-3 that I'm not actually sure how they were chosen. So now that we understand these functions a little bit better, let's actually talk about briefly where they are used in practice. So one of the applications you already know is hash-then sign. Basically, all the practical signature schemes that I happen to know, they're all using hash functions to hash the message into something that's more usable for the signature scheme. The other interesting thing are post-quantum signature schemes. So there's the fear in the cryptographic community that at some point someone will come up with like a huge or like a larger quantum computer. And for quantum computers, there are efficient algorithms for a lot of the stuff that we're usually using. So to prepare for a future where these things may exist in any scale that may come close to breaking our nice crypto stuff, people started coming up with post-quantum signature schemes that rely on assumptions where we don't know yet whether they're broken, but they have a nice chance of not being broken completely by quantum computers. And interestingly, most of the hash functions designs that we have, like SHA-2, SHA-3, they are still okay. And then interestingly, people actually use hash functions as one-way functions. I think we will see later how this is related. And they actually build signatures from it, similar to like the Lampert signatures that you've already seen. And then these signatures only rely on the assumption that this hash function is collision resistant, which is something that would still be true if quantum computers exist. So even quantum computers wouldn't be able to find a collision. So these kind of Lampert-style signatures using hash functions, they would be post-quantum secure, which is why this becomes, like all of this stuff that we're doing right now in the lecture becomes somewhat more interesting right now again. The next thing is that I can use hash functions for just comparison of any of arbitrary stuff. So for example, let's say I didn't have like the certificate from a trusted authority for Fabian's public key, but I just knew the public key. I could just ask him what his public key is, and he could basically read me this thing. However, this takes a lot of time, which is why every certificate and every public key kind of has this fingerprint, which is, well, considerably shorter. This is just the hash of this whole certificate. So if I read this hash to Fabian and Fabian will check whether his hash of his certificate is the same, then I would definitely know, okay, this is the same certificate, the same public key. And I only have to read him this. I don't actually have to read him this stuff. And why is this? Well, for this huge data set here, I can just replace it with the hash value of it, because nobody will be able to find a public key that has the same hash value like this as this. Similarly, on a somewhat larger scale, you can also do things like file integrity. So let's say I've downloaded this huge file. So for example, operating system like Ubuntu. And I want to know whether this download was valid. So whether someone tried to give me a file that's not the official Ubuntu installation, or maybe something went wrong during the download. And I can easily verify this by just hashing this huge file. It takes a few seconds. And then I have this hash value, which I can compare to the hash value that Ubuntu is saying that I should get. And yeah, this looks like it's the same. So hash functions are actually pretty good to even work with huge files and just give me a small thing that I need to compare to make sure that the file is the same that I wanted. Another thing you may be aware of is Git. So this versioning system that many people use, and it's pretty good. Essentially, Git just threw away any idea of maybe I give my commits numbers or something. Maybe I just count up this is the 25th commit or something. This is just, none of this is happening in Git. In Git, you just hash the data for the commit. So the diff and maybe your name and stuff. I'm not actually too sure about this. And then this identifies your commit. So if you take a look at some Git program and you take a look at one commit, it will have the char value, which is the hash value of this commit. And this uniquely identifies this commit. So if I upload a file to the cloud, then essentially the cloud has some interest of if 1,000 people upload the same file, not to store the same file 1,000 times. So if I upload my 2.5 gigabyte Ubuntu ISO file, then chances are they won't actually upload it and they won't actually store it. My client will just tell them, hey, I have this file with this hash here. And Dropbox will just say, oh yeah, I know this file already, you don't have to send it to me again. The next thing is key derivation. So for example, I may have some process like Diffie-Hellman, where in the end, the two parties that have communicated have agreed to some group element g to the a times b. And this group that's used here can be anything. It could be a point on an elliptic curve. In particular, this thing here is not close to a uniformly random bit string at all. It's very structured because it belongs to a very structured group. But then the idea is you can just use a hash function to hash this thing to a bit string. And then you can use this bit string for your AES or something. So to encrypt stuff, let's say. For this, collision resistance is not actually enough. You kind of need that if this is random, then this is random too, which is something that you get, for example, in the random oracle model, which you'll see next week. The next thing is kind of current. It's Bitcoin, where hash functions are used heavily. Explaining this in detail is probably too much for this quick thing here, but they are really central in that they are used as proof of work. So the goal for Bitcoin miners, let's say, is actually to find an X. Such that the hash of this X actually begins with a lot of zeros and then something else. And that's their proof of work. This is used to add new blocks to the blockchain. And just to give you an idea of scale of this, so you can see how many hashes the Bitcoin network. There are other cryptocurrencies, but just let's only look at Bitcoin. So the hash rate is measured in terahashes per second. And we are at 122 million terahashes per second. If you compute this out, you get to a decimal number with like 20 zeros per second. So if we look over the world, then every second there are like a huge number of SHA-2 hashes being computed for this cryptocurrency. It's a huge waste of energy. It's not even funny anymore. But yeah, this is something that's happening. This is something you can use hash functions for. Please don't. And then lastly, you can use them as commitments. So something that I've seen happening is if I want to submit a paper to a conference, essentially everyone is submitting at the last second. And then this Pro server has to handle all of the PDFs that are thrown at it immediately, basically at the same time. And in order to alleviate these problems, some conferences have started having a deadline where you don't have to submit the PDF, but you just have to commit the hash of your PDF. Okay, this is much shorter. This is way easier to handle for such a server. So at the deadline, you have to have the paper ready and completed, and then you have to submit the hash. And essentially, this hash binds you to having to submit the same PDF that you had at the ready at this deadline. Also, when you then later submit the actual PDF, which can be like stretched out for a longer period. Okay, thank you for listening. Sorry for the kind of long list, but hash functions are actually like hugely influential in a lot of what we're doing in crypto. And they even creep into like mainstream apps like Git and like file integrity for downloads, etc. So yeah, it's actually pretty cool. Thank you for listening and see you.